Hi everyone, this is a video about transient or changing current and voltage when you have an inductor in a DC circuit. So this is a setup and I'll just explain what this diagram is all about. So you have a voltage source and this is a three-way switch. So I can have the switch across, I can have the switch in this position. So when it's closed, so when the switch is closed, there's going to be a current through the inductor. I could have a switch this position, or I could also have a switch in between when there's an air gap. So we're going to look at all those three positions. So there's an ammeter here to measure the current, and this VL measures the voltage across the inductor. Okay, so we're going to look at three different situations. One is at switch on. That means the switch is across here, across X, this position. Okay, and then we're going to see what happens when the switch is across Y, so that the inductor is discharging. And then the third one is we're going to look at switch off when there's an air gap. Okay, so slightly different things happen. So let's look at switch on, and then so we're looking at switch on. So when for switch on, you have the current that is increasing. It's going to go from 0 to a maximum. That's going to happen to the current, right? Okay, we're going to do two graphs. We're going to look at what happens to the current and what happens to the voltage. Okay, the current is the circuit current, but my voltage is the voltage across the inductor that I'm interested in. Okay, so it's that voltage, not that one. That stays the same the whole time. Okay, and current is measured in amps, time in seconds, voltage in volts. Okay, so at switch on, it's going to take time. There's an increasing current, so the current is going to take a while to reach maximum. So it's going to go from 0, it's going to be an exponential growth curve. And at some point in time, it's going to reach a maximum. That's a growth curve. Okay, what's happening to the voltage across the inductor? Now at switch on, when the current is going from 0 to a maximum, the voltage across the inductor, the change in current, if you look at the gradient here, the gradient is the most, or it's the steepest at the start, and it gets less and less and less and gets steady. So when the current is changing at maximum rate, that's when you have the maximum voltage across the inductor. So at time 0, as soon as you close the switch, what's actually going to happen is the voltage across the inductor is going to be a maximum, and then it's going to fall and become 0 when the current becomes steady. So at time t0, the voltage across the inductor, like if this was a 9-volt battery, this will also read 9 volts, and the voltage across your resistor is going to read 0 volts at time 0. When the current is steady and it stopped changing, then what's going to happen is when the current stops changing, there's not going to be any voltage induced across the inductor. However, all that voltage will be across the resistor, and that will be 9 volts. You see the change? Okay, so the voltage resistor keeps increasing with time as the current increases, but the voltage across the inductor decreases as the current gets more and more steady. Okay, the current at any instant depends on the voltage across the resistor and the resistance itself. Okay, I'm just going to take these numbers off, but that's what that looks like. And the time constant is the time it takes for the current or the voltage, to change by 63%. So it's the time taken for the voltage to drop by 63% fall, or the current to increase by 63%. And ideally, theoretically, it takes about 5 time constants for this process to be complete. This is what happens at switch on when the current is increasing. My scenario 2 is when you move the switch to position Y. So there's no air gap, right? It's a make before break switch. It's a special switch there. Okay. Now what happens is the inductor has got the stored energy. It's going to discharge. Okay, so this one here, I'm just switch at Y. And this is when there's a decreasing current. Okay, so I'm just going to draw little red graphs just to make it different from the other one. So this is my current time. This is my voltage across the inductor time. So the current is falling, so it's going to be a falling current. Okay, and it'll eventually reach 0. But now if you look at the slope, so the voltage across the inductor is depending on how quickly is the current changing. So if you look at the slope of this, the current is changing most rapidly at the start, right? So the voltage across the inductor is a maximum at the start, and then it falls to 0. So they're both decay curves. Okay, and the time constant is going to be the same for both these. It'll be the same as this. So all their time constants are the same in this scenario. Okay, and I'll come up with a formula for time constant in one moment when I just talk about the third position. Now the third position is when you switch off and there is an air gap. Okay, now air has got infinite resistance, and so the time constant becomes very, very short because T is equal to L over R. T is equal to L over R. So the resistance of air is so high that this becomes very small. So what's going to happen is that the current is going to fall. So this is switch off. Let me just see if you can see what I'm writing on the board. You can. Okay. So I'm just going to draw two graphs. One for current against time, the other for voltage across the inductor against time. So now the difference between these graphs and this one is that the current is going to fall, whatever value it was, rapidly to 0. So this is the time constant is very, very small. So this distance is much smaller than that. It's a very short time constant. And because the time constant is so small, the voltage across the inductor is going to be very, very high. Again, the time constant is very small, and that's why you get your spark across your spark plug. That is why your neon lamps light. Okay, so it's going to be a very high voltage induced, but that also it's like poof, and then goes off. Okay, so that's to do with the graphs. So this one is much higher than any of these. So these, if it was a 9 volt, that'll be 9 volts, that'll be 9 volts. But this could be 90, it could be 1000, it could be a huge number, depending on the inductance and a few other factors. Okay, now just to calculate, just a formula. So for, like I taught you for capacitors, if you need to know for a growth curve, so this is the only one that's growth, all the others are decay. So for a growth curve, your current at after any particular time constant, I equals I max 1 minus e to the power of negative n, where n stands for how many time constants. Okay, that's for your growth curve. All the others are decay curves. For your decay curve, this can apply to either current or voltage. So it can be either. So if it was voltage, it's V equals V max. Because it's decay, it's e to the power of negative n. So that's the formula that you use to calculate the time constant, the instantaneous voltage after any particular time constant. So it'll pay to just read over this page. I've just gone through this page, and once you've understood this, there are these questions on the graph. If you can do these, I'll work through them and put the answers up as well. So I hope that made sense. Bye for now.